Welcome to second order linear homogeneous ordinary differential equations with constant coefficients. So the standard form for what we're considering here is we're looking at equations of the form a y double prime plus by prime plus cy equals 0, where a, b, and c are all constants in the real numbers. So these are all or are real numbers. So the idea that we're going to use here is we are going to assume a solution takes the form y equals e to the r x for some r. Right? So if that's the case, then we have y equals e to the rx. Y prime is r e to the rx. And y double prime is r squared e to the rx. Plugging this in to the differential equation, we would have a r squared e to the rx, that's my a y double prime, plus b times r e to the rx, there's my b times y prime, plus c e to the rx equals 0, or e to the rx times ar squared plus br plus c is equal to 0. Now note, e to the rx is never 0. So this equation implies ar squared plus br plus c equals 0. So this part here is never 0. So that means that ar squared plus br plus c must equal 0. So this is what is called our characteristic equation. So for y equals e to the rx to be a solution, to ay double prime plus by prime plus cy equals 0. What we get is that r must satisfy ar squared plus br plus c equals 0. So this ar squared plus br plus c is what is referred to as the characteristic equation. So anytime we are solving a quadratic equation with coefficients in the real numbers, there are essentially 3 main cases to occur. So the first case is we get 2 distinct real roots. This will occurs when the inside of the square root in our quadratic formula is positive. So this is when b squared minus 4ac is greater than 0. Our next case is we have a repeated real root. This occurs when b squared minus 4ac equals 0. And then our last case would be if we have complex conjugate roots. So complex conjugate roots. And this occurs when b squared minus 4ac is negative or is less than 0. So these are sort of three distinct cases we can work on. Note, in this case, if we have two roots, R1 and R2, then we get two solutions. Y1 equals e to the R1 times x, and Y2 equals e to the R2 times x. If we have one repeated real root, just R1, or R1 equals R2, we only get one solution of this form. Y1 equals e to the R1x. The question is, what on earth do we take for Y2? If we have complex conjugate roots, R1 and R2, we would say R1 is U plus IV, and R2 is U minus IV. We get complex solutions. Of the form Y1 equals e to the R1x, Y2 equals e to the R2x, but these are not real valued solutions. So these are complex valued solutions. So we have to figure out in the second case, what on earth our second solution would be. And in this case, how do we get to real solutions? Or real valued solutions. So in the following videos, we'll look into sort of the individual cases and how we work with them.